Hello, this is PH 4105, Advanced Mathematical Physics, a 4th level course for students in the 4th year or 5th year in the Indian Institute of Science, Education and Research, Kolkata. I am Anandu Dashgupta and I have taught this course several times in the past. And this course primarily deals with two different mathematical objects that physicists need a lot. They are respectively differential geometry and algebraic topology. They are really not altogether different courses because, as you will see as the course progresses, there are several concepts which sort of migrate from one of these topics to the other. But we will begin this course basically with a quick description of differential geometry. So what exactly is differential geometry? To understand that, we will have to take a look at the most important mathematical tool that a physicist needs. Now, there may be some debate about exactly what the single most important tool, at least mathematical tool, that a physicist needs, but I'm pretty sure almost everybody would agree that this is good old calculus. Physicists need to use calculus a lot. Unfortunately, calculus as we know it actually works best for functions which take real numbers to real numbers. Good old simple functions. With some pushing and prodding, you can actually make calculus work in a slightly more generalized sense. Also for Rn to Rn functions, which means these are functions which take a bunch of real numbers, m of them, into n real numbers. However, in physics, we need much more general functions. Functions where the domain and the range could be very, very different. So you would have a function from some set u to some other set v, and more often than not, we will need to do calculus with such functions. Unfortunately, calculus as we know it cannot directly be used in this more general sense, unless you have some help. And that help is actually provided by differentiable manifolds, the star players in our game of differential geometry, which allows us to do calculus in situations where, strictly speaking, you should not really be able to do calculus. So we are going to take a deep look into differentiable manifolds soon, but before we get there, I should really perhaps elaborate on the point that I made, that calculus as we know it can really make sense only for functions of a single real variable to a single real variable. To understand this, you have to go back to your high school days when you first learned calculus. Of course, here I am talking of calculus of functions which take real numbers to real numbers. Recall that one of the first things you learned in calculus was the definition of a derivative. And f prime at x0 was defined to be the limit as h goes to 0 of f of x0 plus h minus f of x0 divided by h. Now there's a surprising amount of structure that you need before this expression makes sense. When you first learned derivatives, I'm pretty sure most of you focused on this part, the limit as h goes to 0. This of course was primarily because this was novel, and also it may not be a priori clear why exactly can you take limits as a number shrinks down to a very small value. And this has something to do with a very technical feature of the real number line, the so-called completeness of real numbers, or more technically, Cauchy completeness of real numbers. However, if you think about it a bit, you will realize that even if you leave the issue of taking the limit out, there are several things in this definition which uses very deep properties of real numbers. These are deep properties, but these are so familiar properties to all of us that we actually take them for granted. For example, one of the first things that you do is evaluate f at x0 plus h. To do that, you have to calculate x0 plus h in the first place. So addition must make sense. Of course it does. You know how to add real numbers. But remember, the whole point of this discussion is to see why calculus becomes difficult to do for arbitrary functions. Functions from arbitrary domains to arbitrary ranges. After all, it's not clear in the outset that we can add two elements in the domain of the function and get a legitimate third element. So this step may very well be the stumbling block. Well, after you are done with this, you have applied f on x0 plus h, which of course would happen because after all this is a function. Give it an input inside this domain, it should be able to give an output in the domain. Similarly, you have to calculate f of x0, but you have to be able to subtract f of x0 from f of x0 plus h. Subtraction must work. And if we are talking of general functions, the addition must make sense on the domain and subtraction actually works on the results of the functions, so on the range. Then we need to be able to divide this by h. Division must work. You should be able to divide an element of the range, the numerator here, by an element of the domain. Of course, here both the domain and the range are real number set, and all we are doing here is divide one real number by another, which is of course perfectly legitimate as long as what you are dividing by is not 0. So all of these work fine as far as functions from real numbers to real numbers are concerned. But you do realize that this is a lot of structure that you need. You need to be able to add on the domain, you need to be able to subtract on the range, and after you do that, you should be able to divide elements of the range by elements of the domain. And this may be a tough ask for an arbitrary function. In fact, if you just went slightly away from functions on the real line and talked about functions from Rm to Rn, you will begin to see what the problem can be. For the time being, I am going to write elements of Rm and elements of Rn, which are ultimately m by 1 and n by 1 column vectors, if you think about it, simply using the vectorial notation. I will put an arrow on top to indicate that what we are dealing with is not a single number, but actually a bunch of numbers. And then we will see how far we can go towards calculating the derivative. Well, here you need to take the f, which is the value of this function evaluated at x0 plus h, subtract from it the value of the function evaluated at x0. I am putting arrows both on top of the argument here as well as f to remind you that both of these are vectors. These are Rm vectors and this is an Rn vector. Now, can you carry out all of this calculation? Well, actually you can. What you need here is the ability to add two elements of Rm, which you know how to do. Rm, after all, has a natural vector space structure. You can add two m by 1 column vectors together. Pretty easy. What about the next step, the subtraction? Well, the result of f is in Rn, and there is a natural way of subtracting. all you do is subtract component by component. Again, the basic vector structure of Rn comes to the rescue here. So as far as this calculation is concerned, things are going perfectly. But if you were to literally repeat what you did for R to R functions, you would need to divide by H, and now you are in trouble. You cannot divide one vector by another. So, even simple job of calculating the derivative actually requires structures which are not present even for functions of more than one variable. Whatever worked for functions of a single variable will not directly work without any changes to these more general settings. And of course, expecting them to work for even more general settings of arbitrary domains and ranges, that would really be a tall order. Now, I did say a while ago that you can actually do calculus beyond the real line, can sort of push it and make it work for functions from Rm to Rn. But as I have just shown you cannot calculate the derivative the way we did for ordinary calculus. We need a new idea. To understand what this new idea is, we will start once again with ordinary functions of real numbers and try to think of a different concept which can generalize to this more general setting of functions from Rm to Rn. Derivatives, as we have just seen, will not work, so we need something new. And that something is also pretty familiar to all of you. That is the concept of the differential of a function. Now, the concept of the differential is essentially nothing other than the simple notion that a small enough piece of any smooth curve is like a straight line. If you were to zoom in on this part of this curve, you would get something which essentially looks like a straight line. That is what a differential actually embodies. And contrary to what you may have gathered from your high school courses, a differential is really not an infinitesimal quantity. Nothing as mysterious as that. It's actually a much better understood mathematical concept, that of a linear map. Now, in order to understand why I am saying that, let's go back to our notion of the derivative. Note that the definition of the derivative essentially means that f of x plus h equals f of x plus f prime x times h plus some correction delta. In this, the delta has to be rather small. In particular, it has to vanish rapidly as this h goes to 0. Note that f of x plus f prime x into h is really the equation of a straight line where h is the x coordinate and this is the y coordinate. F of x is a fixed number, so is f prime x. So this is of the form m into h plus c. Now when I am saying that a smooth curve looks like a straight line, at least a small enough piece of it does, what we really mean is that this delta vanishes very fast as h goes to 0. And what that actually embodies is this concept. If you take the magnitude of delta and divide that by the magnitude of the amount by which you are moving, that is h, this ratio has to vanish in the limit in which mod of h goes to 0. Now, there are some points we must make about this. This quantity f prime x into h, what is this really? It's just a single number, but it is the value of a map that takes h to f prime x times h. Now this map, simple multiplication by the number f prime x, is actually nothing but a linear map. It is one of the simplest possible linear maps. Is a linear map from R to R. And what we are going to do is use a rather complicated looking notation for this. We are going to call this df bar x, where the bar x simply means that you are evaluating the differential of f df at x. Now putting all this together, we can actually give a different definition of differentiability of a function at x. This is of course once again a function from R to R, and it's not really a different definition, it's just an equivalent one. And the definition goes as follows. A function f from R to R is differentiable at x, of course a point in R, if there exists a linear map, the so-called df at x, which is again a linear map from R to R, our map which changes h to f prime x times h, such that the following happens. Mod of f of x plus h minus f of x minus df at x acting on h. Remember, this is nothing but f prime x times h divided by mod of h. This quantity is nothing but the ratio mod of delta by mod of h, and our statement that a small enough piece of a curve looks like a straight line essentially translates to limit of this quantity as h goes to 0 is 0. Now, if such a df at x exists, such a linear map exists, we say that the function is differentiable, and df is of course what we call the differential of f at the point x. Now, the reason why this particular reformulation of the definition of differentiability is so important for us is that it actually can be generalized rather trivially to the case where the f is not a function from R to R, but a function from Rm to Rn. Note that if we are considering f to be a function from Rm to Rn, we can still use this definition almost entirely as it is. All we have to do is change the domain of f to Rm, the range to Rn. Similarly, dfx will now be a linear map, not from R to R, but from Rm to Rn. And the quantity that you are going to calculate here will essentially be the same quantity, except for the fact that x, h, etc. here will be vector valued. And you would still have a problem with dividing by a vector, but that's no longer a problem here, simply because what you are going to divide by is not the vector itself, but the length of the vector. Similarly, what goes in the numerator here is not actually the vector, but its length. So, the definition actually becomes this. A function f from Rm to Rn is differentiable at x belonging to Rm if there exists a linear map df at x from Rm to Rn such that this thing holds. Now, what I have done is drop the arrows we put on top of elements of Rm and Rn earlier. We are just going to write x where x is a m tuple of numbers, so is h, and this of course is component by component addition, just like the standard addition on Rm and so on. Notice that this definition makes perfect sense because what you have in the numerator here is actually a number, the length of this vector in this, and similarly you have a number in the denominator, and you can of course divide a number by a number. And you can take the limit in which the denominator goes down to 0. If this limit happens to vanish, then what you can say is f of x plus h is very well approximated by the linear approximation of f of x plus d of f at x acting on h. And this is the generalization to the statement that a small enough piece of a curve looks like a straight line. In higher dimension, it would be a small enough piece of any surface, as long as the surface is smooth, looks like a plane or a hyperplane, if you're talking even higher dimensional surfaces. The linear map df at x, if it exists, is called the differential of f at x. Let us now take a closer look at this linear map, and we will begin with a simpler situation where f is a map from Rn to R. It's a real valued function of n real numbers. So df here, or strictly speaking df at x, is a linear map from Rn to R. And any linear map from Rn to R must be of the following form. If you apply df at x on h, you must get a linear combination of the elements of h. H has components h1, h2, h3 up to hn. For reasons that will be clear soon, we write those indices not as suffixes but superfixes. So these are not powers but indices. And you have to multiply h1 by a number, h2 by a number, hn by another number, and add them all together. This is what d of f at x acting on h is. Basically because this is going to be the form which any linear map acting on a vector on Rn will be. What is important here is that the coefficients d1f at x, d2f at x, up to dnf at x completely determine what the linear map is. And these are called the components of the differential map. And by adopting Einstein's famous summation convention, we can write this as dif at x times hi, where a summation is implied whenever you have a pair of repeated indices, one upstairs, another downstairs. In fact, it is because of this upstairs downstairs rule, we had to put the indices here as superfixes and not suffixes. Now, what exactly is this quantity dif at x? It happens to be something pretty familiar to us. To see this, let's consider a special case. Let's consider h to be a vector for which only the first component, h1, is not 0, all the others are 0. Let me stress one thing here. As far as d of f at x acting on an argument h goes, this h does not have to be a small vector in any sense of the word. H can be a pretty large vector. A linear map will definitely act on that. The only point is, if h is a large vector, then the approximation that f of x plus h is given by f of x plus d of f at x acting on h is not really going to be a very good approximation. That approximation is going to be better and better usually if h is a vector of a small length. But other than that, there is no reason to demand that the length of h in general and h1 in this particular case is small. At the end of the calculation, what we need to do is actually take the limit when the length of h, which is just the magnitude of h1 in this case, goes to 0, and therefore, in the end, we will need a small vector. But the point I'm trying to make is df at x can act on large vectors or small vectors. It does not distinguish or discriminate between vectors on the basis of their size. Now, the demand that we have on df here simply becomes the following. F of x plus h, here h of course is just h1 with a bunch of zeros, minus f of x, minus d1f at x times h1. Note that because h1 is the only non-zero component of h, df at x acting on h simply becomes d1f at x times h1. So this is the numerator that you have in our definition for differentiability. Of course, what we need to do is take the norm of this quantity. But here, remember, f is a map from Rn to R, so the numerator is really a real number. So the norm here simply becomes the standard magnitude or mod. Similarly, what we need to divide that by is the length of the vector h, but the length of the vector h is simply the modulus of h1 here. Now what we need to ensure is that when this norm of h goes to 0, this whole ratio has to go to 0. And that actually can be rewritten very simply as an expression for d1f at x. d1f at x will simply become the limit of f of x plus h, which is f with arguments given by x1 plus h1, x2 plus 0, x3 plus 0, all the way down to xn plus 0, minus f of x, which is f at x1, x2, xn, divided by h1. So all I have done is taken this thing, stated that this goes to 0 rather fast, and then taken d1f h1 to the other side and divided by h1. The fact that this ratio goes to 0 means that whatever is left after you do the division by h1 still goes to 0 in the limit h1 goes to 0, and therefore this is exactly what d1f at x is. Now this should be a very, very familiar quantity from at least first year maths. This is exactly like the definition of a derivative, but here we have a function of n variables in which all of n minus 1 variables x2, x3, xn are held fixed, and only x1 is changed from x1 to x1 plus h. So this is nothing but the derivative we get when we pretend all the other arguments, the second, third, fourth up to the nth, are constants, and only the first argument is a variable. In other words, this is nothing but the partial derivative of f with respect to x1 at the point x1, x2 up to xn. So the coefficients that we have in our differential, at least for a function from Rn to R, are very, very simple quantities. They are nothing but partial derivatives of the function f evaluated at that particular point x. This was about the first argument x1, but simply by taking h to be 0, h2, 0, 0, 0 or some other such value, we can actually show that dif at x is nothing but the partial derivative of f with respect to xi at the point x. At this stage, let us pause briefly and try to connect what we have been doing so far with our notion of the differential as an infinitesimal change in a quantity. Note that h1, h2, hn are components of the displacement that you are carrying out in the domain. You are moving from x to x plus h. If you consider these displacements as infinitesimal quantities, you would prefer perhaps writing dx1, dx2, dxn for them. And then the result that we have obtained for our linear transformation simply tells you that df, the change in f, should be d1f at x times dx1 plus d2f at x times dx2 and so on. But notice that d1f at x is nothing but del f del x1 in our old notation for partial derivatives. So what we really have is our familiar old rule for the total differential. df is del f del xi dxi summed over all I. However, we are not really going to use that notation for one very important reason. We are actually reserving the notation del f del xi for a related but slightly different purpose, which will be clear once we start talking about tangent vectors. So since we are going to use these more familiar partial derivative notations for a different purpose, we are going to stick to di of f for the partial derivative of a function f with respect to the ith argument. So let us now go back to doing calculus once again, and let us now move on to a more general class of functions from Rn to Rn. Now, if a function f is from Rm to Rn, you can equally well think of this as n separate functions f1, f2 up to fn, each of which are functions of m real variables. And therefore, when you talk of dfx at h, you are actually talking about df1x acting on h, df2x acting on h, and so on all the way down to dfnx acting on h. And it makes sense to write them all in the form of a vector. In this case, I have written them as a column vector. Since f1, f2, f3 and so on all the way down to fn are each functions of m real variables, we can use whatever we have learned just now about functions from Rm to R to write down the expressions for df1x acting on h, df2x acting on h and so on. And df1x acting on h, as we have just seen, is nothing but d1 of f1 at x times h1 plus d2 of f1 of x times h2 plus all the way down to dm of f1 at x hm. And there is a similar such line for each and every one of the dfi's. This of course means that I can write the action of df at x on h as the action of a matrix acting on a column vector with elements h1, h2, h3 down to hm. In other words, df, the linear operation, can be represented by a matrix. And this is a very, very familiar matrix to all of us. It's nothing but the so-called Jacobian matrix, which is formed by taking the partial derivatives of all the functions f1, f2 all the way down to fn with respect to the variables x1, x2, xn and putting that in a n by m array. Of course, you may be more familiar with the Jacobian matrix written in the form where the elements are del f1, del x1, then del f1, del x2 and so on, del f1, del xm, and then all the way down to del fn del x1 to del fn del xn. But as we have just pointed out, this notation means exactly the same thing, and this is the notation that we prefer to use in this course. Let us now move on to one more question of a function whose domain is not exactly Rm but some subset u of Rm. So we are talking now of a function from u to Rn where u is some subset of Rm. Of course, I can again think of this function f as a bunch of n functions f1, f2, fn, each of which map u into R. So frankly, thinking of functions from a subset of Rm to R is all that you really need to do. But in any case, what we need to do in order to define differentiability for such a function is that you have to be able to make sense of the quantity f of x plus h for all x which are there in u, at least as long as the length of the vector h is small enough. After all, if you cannot apply f to x plus h, then the issue of f of x plus h being approximated very closely by f of x plus df at x times h acting on h simply does not arise. Now, for this to work, what must happen is that at any given point x, there must be some leeway so that you can move a distance away from x in whichever direction you want, and you would still be within the set u. In other words, there has to be a ball of some finite non-zero radius surrounding x, which is entirely contained within u, as a result of which f of x plus h can be well defined at all points inside that ball. So this can of course be interpreted as the statement that x is an interior point of the set u. All the points of u has to be interior points. So in order that the definition of differentiability as we have written down makes sense for the case where the domain is a subset of Rm, what we need is this subset u must be an open set of Rm. This is going to be critically important in the definition of the manifold, something which we are going to study next. Let me point out that you can of course talk of situations where the domain is not an open set, it also has some of its boundary points, but then you will not be able to talk about differentiability at those boundary points. This actually becomes an important issue when we begin to talk about manifolds with boundaries later on in the course. For the time being though, we will talk about ordinary manifolds, and there open sets of Rn is going to play a very important role. Just to give you a peek preview of this, in the next lecture we are going to define what is called a manifold, and there you will need to talk about things called charts. And what you need to appreciate at this point is the fact that here a chart is a set U which is a subset of the actual set M, and phi is a map from U to Rn. This map has to be 1-to-1, and what is very important is phi of U has to be an open subset of Rn. We will see in the next lecture how this notion of a chart allows you to talk of coordinates of a point on a manifold, and also how you could exploit these charts to start talking about differentiability of a function when the domain is some manifold and not some simple subspace of Rn. But all that is for the next lecture. Bye for today.